let's pick up from our conclusion of last night's lesson that somehow introduced us to the understanding of the shape of collider events in terms of first principles. So in terms of the basic principle with which we can calculate the dominant radiation in that environment, which is QCD radiation. And we also commented about what happens if we include everything. So if we include not only QCD, but the entire standard model. So the picture that we came up with was a picture that in the, and let me refer now to the specific process that we worked with. There was any plus and minus process. So for the process that had the plus and minus going to QQ bar, remember? So we came up at the end having calculated an event shape of this kind. So we could understand, and if we had to draw what would happen in nature, so what would happen in the collider after the collision, we would draw something of this kind. So we would have a back-to-back hard pair of quarks, the QQ bar coming out, and then starting radiating in many different ways. And what we calculated, of course, was just the first step of this chain of radiation. So we calculated just something like this. But we didn't go any farther, but that can happen. So you can imagine that you keep going at all orders, order by orders, and this is what keeps happening. So the first one is emitted close to the hard parton, and then it becomes the hard parton itself, and it emits more, always close to its original direction, and so on and so forth. So we came up with a picture of this event that was very much concentrated in a region around the direction of the hard partons. So a region that has a sort of shape of this kind, right? And so we could explain if we had to, if you want guess, or if you had to tell what the shape of the event, what kind of event you would have in your collider, you would say, I have produced two cones, if you want, of hard, strong activity, right? So strong interaction activity. That is typically what we are now used to call jets, right? So this is really what brings this event and this process to be a process in which we normally say we have an event that is an event of E plus E minus going into two jets. Now, what we did here, there was just to calculate this process sort of exactly, not exactly, justifying this shape exactly at order alpha s. Of course, it can be repeated at higher orders. So as I drew here, you can start considering radiation that is emitted over and over. You can start adding the corresponding virtual corrections over and over. And the compensation, if you are inclusive in your radiation, if you are inclusive in the process that you are considering, keeps happening. And so you get to calculate something that has a finite cross-section. And the interesting thing that we saw yesterday is just that in the soft collinear region, this process is very systematic from the point of view that you can build the next order in terms of the previous one. So you can build the n plus 1 process in terms of the n process. And in fact, we built the n plus 1 that for us was the QQ bar plus 1 gluon in terms of the QQ bar. And we isolated a sort of probability factors, or if you want, radiation kernels, if you want, that are the ones that we use in order to build in the soft collinear region, not all over, right? So I'm not saying that I can calculate the cross-section for E plus E minus to QQ bar gluon as I'm writing out on the blackboard, because that is something that is not factorizable in terms of the previous order. But in the soft collinear region, which is the region that dominates the shape of the event, it is. And as you remember, we had established, if you want, that I can now summarize, if you want, the result of the Langish calculation that we had last time, that we had yesterday, in saying that if I have a process that is whatever it is, sort of an X hard process, with a lag that is a quark, and this lag emits a softer collinear gluon, that has a momentum k, while this has a momentum p coming out, I know how to calculate in the soft collinear region. So if I here look at the soft collinear region, I know that the cross-section for this guy can be calculated multiplying a factor that we calculated together at the 2 alpha s CF divided pi, remember? And then if I write it in a differential way, this was the d omega k over omega k, where I remind you that the omega k was the energy of the k coming out. And, sorry, the d theta of, if you want to call it kp, this angle here, over theta of kp. This is the factor that we calculated together yesterday. So if I wanted to write the entire cross-section, this will be the integration of this factor multiplied by the sigma QQ bar cross-section. So once and yesterday we worked at the integration of this factor, and we justified the fact that the infrared part of this object is cut proportionally, so is regulated by the presence of the virtual correction. So this integration, as a matter of fact, is a finite factor that comes in front of the sigma QQ bar, and is what we could call a radiation probability kernel. Now, I also told you that the same would be true even if I had a gluon here. So if I had to consider an X process, and in this case here for us, this was the sigma QQ bar, but I could also write it just X, if this is my X hard, let's call it hard process, which in the example that we had here, we had X equal to QQ bar. And the same would be true if this had to be a gluon that we didn't do together. We didn't calculate it together just to avoid having to deal with the triple gluon vertex, which is more complicated, et cetera, but nothing is different. It's exactly the same thing. So if I had to do this very same calculation, this would be exactly the same thing, except that here I would have, as I told you yesterday, a different color factor. And the rest would be exactly the same. So this somehow brings us to think that we can build a sort of, if you want, systematic, we can systematize in an algorithmic way the generation of all these multiple layers of radiation. And this is exactly what parton showers do, right? So what parton showers do, they calculate a probability kernel, which is exactly the ones that I wrote here, attached to each single branching that you have in the shower. So you have to imagine that attached to each single point here, you have the probability kernel for the splitting that is characteristic of the branchings. So that could be a quark going into a gluon and a quark. It can be a gluon going into a gluon and another gluon. It can be a gluon splitting into two quarks that we haven't looked at and haven't drawn over there, right? So attached to each single dot here, you have your probability, and you just probabilistically generate it in a Monte Carlo fashion from the energy Q of your hard process to some lower and lower and lower energy, and of course this happens on both sides, in which you go systematically through stages of lower and lower energy till you hit, let's say, a Q0 final energy, which is of the order of lambda QCD, where you have to have something in place to hadronize your partons, right? So this is the place where our knowledge, as I emphasized in one of our first lectures, of what is happening exactly in perturbative QCD plays a role. As you notice, it's not exact, right? So it's not that we are calculating exactly what is happening. As I emphasized many times, we are picking the dominant part of what is happening. But the reality of colliders events, when you look at them, tells us that we are on the right track. Because indeed, when you look at the hadronic activity in a collider, and you have to imagine that what is coming out here is exactly what is picked up by the different layers of detectors that you have in your collider, has exactly that shape. So there is mainly activity in a collinear direction, so around the hard tracks that came out of the interactions, kind of dressed minimally by some soft activity, and there are occasionally some soft activity and even sometimes a hard activity at very large angle, but very, very rare, right? So this is something that gives us confidence that if we can systematize what our calculation has told us, we have a way to predict or to model in something that is not just tuning parameters, the shape of colliders event to a very good approximation. Well, very good, it depends on what you mean by very good, meaning that what we have done yesterday, today is not considered to be exactly very good, right? Meaning that we have just to look at what happens at the first emission, not further than that. Now, nowadays, and this is what would be the, if you want, the leading order implementation of a shower. So today we normally calculate everything that comes into here. So we repeated the calculation that we have done yesterday in first approximation at higher orders. So considering higher order of emissions, and wherever we see contributions that are large, like for instance the logarithmic contribution that we have seen yesterday, we have ways looking at, as we will see, the running of these kernels to resum some of these larger logarithms that come into our prediction. So clearly, the mechanisms that we have seen together can be improved. Now, the only thing that cannot be improved by adding extra layers of QCD corrections to these, that means repeating the calculation at higher orders, is the fact that we are making an approximation. That is good, but it's still an approximation. So the fact that we are just looking at a region of phase space that is a soft or collinear. Now, depending on the process that you're looking at, you may be interested in a process that has several hard objects and several hard emissions. So you may be interested, you may be looking at, for instance, you're looking at this event here, and you see that there are a non-negligible number of events with 3 jets, for instance. And at that point, clearly, calculating things as we have calculated them here, and hoping to see a 3rd jet described by the shower will not be exactly a good approximation. But first of all, what we have to do here is just to define, because I keep using the word jet, but I haven't really defined it yet, right? So let's define that very briefly. So I'm not giving a lecture on jet physics here, because it's a science in itself, right? Like Parton showers are a science in themselves, right? But so that connects quite interestingly and importantly to what we have discussed, because when you want to define something that is sound, that is applicable to the description of physical phenomena that you are reproducing at colliders, you want to make sure that what we have seen in our calculation, so the fact that there are no oddities or ill-defined objects in our calculation that blow up when we go to small angles or to small energies, because otherwise your prediction doesn't make any sense. So this nice cancellation that we have seen in our calculation happens because we have considered everything. Because we are integrating over the entire phase space, and we are considering all the objects that are coming in. So we are considering QQ bar together with QQ bar plus a gluon, and if we go on, et cetera, et cetera. If we start being more picky in our definitions, or if we start picking observables that are more special, this may not happen. So the crucial distinction and the crucial thing that you have to ask to any collider observable when you want to measure it, or when you want to define it, when you are thinking of what is the best observable that I can use in order to study this particular theory or this particular model, make sure that it is what we say infrared safe. Right, and so make sure that infrared corrections do not introduce, if you want to make sure that the cancellation of infrared divergences that we have seen can happen. So this is important when you define a JET algorithm, because some JET algorithm may not be infrared safe. And what that means is just that typically the natural way to defining a jet algorithm is just to define a cone around your hard pattern and say that you lumped together or you combine anything that is in that cone. Now, you have to make sure that if you have a jet algorithm that whenever you emit something soft in between, doesn't all of a sudden combine these two jets into one. Because otherwise, your event all of a sudden can go from an event that has two jets to an event that has only one jet. And so whenever you look at the definition of different jet algorithms, this is an important point that is normally considered. This was just an example to tell you. But how we define jets is exactly in this way. So, what you do is, so we understand that the hard objects in our process are the important ones. So if you think of, and we understand the infrared dynamics. So you wanted to find something that is infrared safe to define. And so it looks like, from what we have, and you can prove that what we call the flow of energy is infrared safe. Because once you define the flow of energy in a given regional space, soft radiation in that regional space does not modify the flow of energy in that regional space, and collinear radiation in that regional space stays in that regional space, does not modify the direction, right? So because of that, now the flow of energy, you can say where, right? So you want to define then a regional space in which that energy flows, and looking at what the shape of your event is, the natural way to define it is just really in these cone-shaped regions that are the one in which the radiation is concentrated. This, of course, implies to define a distance in your collider space, and that distance, so this will be in the around the hard patterns in a region that is defined by introducing it has to use natural coordinates for your event, so it has to use natural coordinates for your collider, where this is the axis of the collider at this point, and this is the direction of the axis of the collider, as well as this is the azimuthal angle around the direction of the collider. And it also has, if you remember what we said, and not for the case of E plus E minus, but if I now consider here the case of PP, we also are working with a system that in the center of mass is not the same as in the lab, so the system in the lab is boosted with respect to the center of mass. So what we pick as our definition better be boost invariant, right? So because of that, we have to go back a little bit to something that we have not introduced at the beginning, but just something that I think is important at this point to quickly, very quickly review for ourselves. Is just to what is boost invariant and what is not boost invariant in a collide for among the observable that not the observable, but the variables that you normally use, the kinematic variables that you normally use in describing your events. So if you have so let's open this parenthesis very quickly. So what I wanted to justify is just why we define the region around the hard pattern in terms of a distance that we call a radius, r or delta r, that is defined this way. So is normally defined as if you have two objects. So the two objects, I and j, will be, let me call it age for hard pattern, and j will be the emitted object, will be the y h minus yj square plus, I will define in a second what I'm writing, the phi h minus phi j square. So what this y is what we call the rapidity of an event, and the phi is the azimuthal angle. So it's the delta y between the two square plus the delta phi between the two square, and then, so it's a radius in this rapidity azimuthal angle. Now let's see what is the meaning of that geometrically also. It's described exactly, we will realize that it describes the cone that our radiation occupies. And let's justify the fact that this is a definition that is indeed boost invariant. So it's a good definition when you calculate things in the center of mass, and then you want to translate that to the lab frame, which is where you put cuts on your jets, because that's where you work, right? And jets typically are defined in order to make sure that you can see them. They are defined in such a way that you can isolate them from the beam direction, so that they're really in the transfer direction of your experiment, so of your setup. So how you write the boost in the z direction? So the z direction, remember, is the direction of your beam. So this is the z direction. Now, if I have to write the boost, I will say that the energies, two things, if the boost is a boost in the z direction, because remember that we have an imbalance between the momentum of the two partons coming in, because one is a fraction x1 p of the momentum of the first hadron, and the other as a fraction is 2p of p1 and p2, and even if the two p's are equal, it's just the two different fractions of the momentum of the hadrons, will go, so the energy will transform. The x component of the momentum will not transform. The y component of the momentum will not transform. And the z component of the momentum will transform. And they will both transform with the hyperbolic sine and cosine of the beta parameter of your boost, so your boost parameter. So the energy will transform into something that, let's say, is the hyperbolic cosine, the energy, the original energy, let me write, the hyperbolic cosine of beta times E plus the hyperbolic sine of beta times Pz. And the Z component will transform with the other combination of E and Pz. So you immediately see some things. So you see, for instance, that phi, right? So the angle phi of, these are the coordinates of a generic object. So it could be the coordinate of H, it could be the coordinate of J, it's the coordinate of any object, any parton in your frame. So immediately see that phi, the azimuthal angle, that you obtain as the invert tangent of P sub x over P sub y over P sub x is invariant, right? Because P sub x and P sub y do not transform as we saw there, as we see there. Now we need to define what the rapidity is. So the rapidity, well, you saw, of course, not only phi, but the transverse momentum, which is the combination of these two components. So the PT is also boost invariant. So the PT is boost invariant. So good. And that's why we use all these transverse momenta, right? And the phi is also boost invariant. The rapidity that I haven't defined it for you, but I will define it now as a half of the logarithm of E, and you will see why the logarithm. Half of the logarithm of E plus P sub Z over E minus P sub Z. Of course, you see immediately that is not boost invariant, because if I substitute inside what happens under the transformation, I see that this goes into, sorry, a half, so the argument, and then I'll take the log, the argument goes into itself, but times a factor, right? And the factor is the cosine, hyperbolic cosine plus hyperbolic sine divided the difference. If you normalize, if you rationalize the denominator, you will get something that is the hyperbolic cosine square plus the hyperbolic sine square. Sorry, the hyperbolic cosine plus the hyperbolic sine, the whole thing square. So this is what the argument of this log goes into, which means that the logarithm of these transformed argument transform into the sum of the two. So you reproduce the rapidity, from the logarithm of the first term plus a factor that is a half the logarithm of this guy. And since it has a square, it's the logarithm, let me say, of c plus s, where c and s are my hyperbolic cosine and hyperbolic sine. That means that the pseudo rapidity by itself is not boost invariant. So this is not, or if you want, I can say not boost invariant. But the difference, or rapidity, the delta y is, because the transformed one has only a constant factor with respect to the other one. So this guy, so the delta r is good, okay? So that if I define a jet in terms, so if I define any geometric region in terms of this delta r between h and j, I have something that goes as such between different frames. In particular, it goes as such between the center mass frame and the lab frame. So this is an object that I'm fine using because it's boost invariant. So for hadron colliders, it's a good object to have. And that's why you define all jet algorithms in terms of this delta rj, which is in a space. One thing that we wanted to notice is just that this pseudo rapidity in the limit of massless partons, and that's not a particular limit to take because most of the partons, we can take them as massless. And even when we go to heavy quarks, at the energy of the LHC, in first approximation, that's not a bad approximation, I would say. So when you take the massless limit of this quantity, well, the E and component of the momentum becomes the same thing. So what these modulus a cosine theta for PZ. So what this becomes is the half of the logarithm of 1 plus cosine theta divided 1 minus cosine theta. And it becomes a really geometrical quantity because this guy, modulus some trigonometry, I think is 1/2 the log of something that is the cosine square of theta over 2 over the sine square of theta over 2. So this becomes the log of the cotangent of theta over 2. So it's an angle, right? It's nothing else. It's a function of an angle, right? Such that this really describes, if you notice, if this is your axis orthogonal to your beam axis. So let's see what happens. So when you have, so if you measure your angle from here, so when you have theta equal to 90, that is a 45. So you get the log of 1, so it's 0. So you get here at 90 degrees, you get theta equals 0. And then, of course, as you understand, theta grows in this way, right? So, and it grows not too fast, even if you get to angles of 40 degrees, like something like here. Eta, I think, is probably between 1 and 2. I don't remember. I think at 40 degrees, is somehow I have this number in mind. Yes, it's 1. At 40 degrees, you can calculate. So eta is 1 when theta is equal to 40 degrees. And even when you go down to much smaller angle, so by the time you are here, you're probably eta equal 3 by the time you are at 10, 15, 20 degrees, right? So large eta is really very, very close to the beam. So, and the phi, I haven't drawn it, but the phi is the angle that goes around the direction of the beam. Yes?
What is the relation of eta with y?
Sorry?
The relation of eta with y?
Eta with y is just the massless limit of y. Okay. So eta is the massless limit of y. So yes, so when I went from here to here, I'm just taking the mass of this object going to 0, and you see that the E factor out, and you're left with the 1 plus cos theta divided 1 minus cos theta. So this is a kind of important to realize because it gives you also an idea of some of the cuts that you use, right, in experiments, not all of you, but the experimentalists of you and whoever does phenomenology. You see that typically jets have a cut on PT, and they have a cut on rapidity or pseudo-rapidity more typically. That is, to a first approximation, the very same thing, right? And the rapidity normally is around 2 point something, and occasionally goes down to 5. 5 is huge, right? Because when you get to 5, you're probably saying that you are sensitive to things that are very, very close to the beam direction. So you really have to have an incredible detector performance to really be able to use that region or forward region, that as it's called. Most of the time, you limit yourself to a region that is more or less here, that is quite transverse. So a region in which you can really see the shape of things away from all the mess that is going on in the beam direction. And so in theta and phi, you can also see so if you have anything coming out in any direction here, if you have a parton, a cone, an R direction in the phi eta plane, it just means that you take a cylindrical surface around this object, which is your beam, right? You unwrap it, and you look in this theta phi plane to where the energy depositions of your partons are. Those are the coordinates of the collider. So this surface around your beam becomes one of those planes in which you then see plots that are all divided into little squares. That is the grid that you use for your eta, which is y and phi. And you see these famous Lego plots in which you represent where the energy of your detector has been recorded, which corresponded to the energy deposited by these guys. So a shape on this surface corresponded to the cross-section, to the transverse section of a jet, so correspond precisely to this distance that we see over here, right? So a naive cone jet is a cone jet that says, my jet is defined as a jet that has delta R, ij, among all the constituents. So I define that in such a way that anytime the distance between the hard original parton and any other parton is smaller or equal to some prefixed value, I combine those objects. And that becomes one and the same thing. So it becomes the energy of the new combined object. This can be defined in more sophisticated way. So this is probably, I would call a naive jet algorithm. There are more sophisticated ways that weight these delta R ij in order to obtain more regular shapes in this projection on the PT of the component. So it takes, for instance, it multiplies these by a weight factor that is maybe the minimum between the PT of the hard object and the PT of whatever else is there. And you know, here it seems redundant because you say, you know what the hard object is. Well, when you have a lot of seeds in your detector, you have to determine, you have to compare all of them, and you compare them with this kind of algorithm, in which the prefactor can be the minimum between the PTs of the objects that you are considering, or the inverse of the PT. And this choice that goes under the name of KT, an anti-KT jet algorithm, as you may have heard, is just something that allows you to regularize more and more, depending on the process that you are considering, the shape of these objects. Sometimes when you look at this plot, you will see that the energy deposition is bizarre. It has a form that is like this. But if you use another jet algorithm, it becomes much more regular. And so it's easier, in a way, to identify the shape of your object. So this parenthesis, just to tell you that observables has to implement and realize the condition that we have seen in formulas yesterday that worked for us because we were very inclusive. It may not work always depending on the observable that you are considering. And one of the good observables that realize that condition is a very inclusive one, that is the flow of energy. But this also has to be defined in terms of the flow of energy where. And therefore, this is what brought us to introduce the concept of a jet and what in experiments we call a jet, and how this is something that also we try to reproduce theoretically. And as you may imagine, parton showers are pretty important in reproducing these objects. Because if I had to do what we call a fixed order calculation, so if I had to stop with my calculation to where we stopped yesterday, so calculating QQ bar and QQ bar plus glue, I would have a perfectly fine object, because it's finite. I can calculate it till the end, including the regions that I have not calculated on the blackboard yesterday, so all the finite contributions. But at the end, what would be the jets coming out of my calculation? I have 3 partners in the final state in my fixed order calculation. So I could, most likely, 2 of them will not recombine because they will most likely almost back to back, even when I insert the 3rd object. So I would have most likely either 3 jets made of 1 parton each, or I will probably have 2 jets, one made of 1 and the other made of 2, which is really hard to compare with what the experiment sees, or not particularly predictive, because you know, it's what it is. It's just made of 3 objects, while in experiments, you guys see nature. Nature is not made just of 3 partons. It's made of whatever strong radiation comes out of the original process. So this is the value of putting on top of that a parton shower and defining something to rule it. Because you put on top of that a parton shower, you start emitting radiations. You want still to map whatever comes out to jets, right? So to what the experiment sees. And this is how you do it. So this is with an algorithm that then implemented that for you. So the parton shower algorithm that are normally, so this is just to define, to connect to what is done with the result, if you want, of a parton shower. As far as the parton shower goes, we said that those are the fundamental building block of the process, of the algorithm. And how they're used by building step by step the emission with what I was saying, a probability that is proportional to these kernels every time I get to a branching. So every time I emit a new object till I get to an energy in which I have to interface with some hadronization algorithm. So I have to interface partons with hadrons with some criterion, okay? Now, to give you a little bit more of information about what goes into the parton shower algorithm, as I said, I'm not really going to go into any detail, but I just wanted to tell you just how the thing is calculated a little bit. You need, first of all, an ordering in the emission of your radiation. So most likely, the energy is degrading in going down, and the emissions becomes, if you want, to softer and softer. So if the emission becomes softer and softer, also and remember that we are building it out of a collinear approximation. So we are looking at, in the kernels that we have there, we are looking at the energy and the angle. Now, there is a quantity that is related between both that is related to both of them. That is the transverse momentum of this object. That is just the energy, omega k, times the sine of this angle. And for small angles, this is just the product of the two. Right? So it's omega times theta. So shower algorithms are normally ordered either in KT or in angle. Right? And so you, for instance, if you order them in KT, it means that at different stages, you go from a higher KT, let's say KT1, to a KT that is smaller and smaller and smaller till you get to your Q0 that is of the order of lambda QCD. And in each of these windows, your radiation is bound by the window itself. So you separate in stages your emission. So you start from the Q scale of your hard process, and then you go down. So the first interval will be between Q and KT1, and then you will go from KT1 to KT2, and et cetera, et cetera. And in each interval, you calculate what you are interested in is the probability of emission, and you're interested in writing something that represents the overall probability of emission, or sum the probability of emission in that window. So what you actually calculate, so you calculate the probability, what you're interested in is the probability, for instance, in the first window of the emission for a KT that is above KT1. And then in the second one will be above KT2, in the third one will be et cetera, the last one will be about lambda QCD. And you calculate it, rewriting it as 1 minus the probability of non-emission. And you say, why do you do that? Of KT bigger than KT1? Well, because this is what we have calculated, the probability of soft and collinear emission, that it doesn't go above a certain KT1. So we know this formula, which is here. And if we repeat this process over and over for all the different stages, we get an exponential iteratively. So we build what is called a delta KT, let's say Q0, so that goes from the Q to the Q0, which is, or if globally, and for each little stage, we just build these kernels that we attach, let's say the first one will be this one, right? That will be just the exponential of a factor that is minus 2 alpha S CF divided pi times the integral of what we have there, the d omega k over omega k, and the d theta kp over theta kp, with a step function, so with a condition that tells us that it has to be above kt1, so that the theta kp that I've used here times the omega k has to be above the kt1, which is the first one that I'm chosen. And then you combine these with all the others, so this factor that we call Sudakov factor is the probability that is used in the algorithm of Parton-Shower at each single little node that you see here. And you combine them all in a Markov chain, Monte Carlo, et cetera, et cetera. And so in a statistical environment that assure you that the overall probability of emission is 1, that you're not making the universe exploding for gluon radiation, and, and some other kinematical constraints that you impose, because of course the emission of radiation has to conserve energy and momentum at each single node. It has to conserve energy and momentum globally for your process, and et cetera, et cetera. And this builds for you the steps from the simplest one to the more complicated one that you can also, the simplest one you can also write with a few lines of code, of the radiation that will generate the jetty structure of hadronic events. So the next step that we will just mention, but not particularly discuss in detail, because again, this is something we need to make choices in what we want to discuss or not, and this is something that is not entering with particular relevance in the discussion that we are going to have, is the step of hadronization, right? So Parton showers, event generators, that are the ones that implement the algorithm that I just described, make choices. And one of the choices that they make is not only the statistical environment in which these proliferation of radiation is implemented, but they make choices also on the final step, which is the hadronization step. So how, at this level, when you get to the level of Q0 equal to lambda QCD, you map partons into hadrons. So some principles are common. So first of all, what are these objects? You may have names in mind. So popular objects are objects like Pythia or Herwig or Sherpa. These are the 3 names that always come up in all collider experiments or collider analysis. They have been developed over many, many years. They're all based on this discussion that we are having right here. They, of course, have technical aspects that are specific to each one of them, but they are a further complication layer that are not really changing the fundamentals of the discussions that we are having here. One of the things they differ on is this one. So the mapping from part to hadrons is based in both cases on a sort of one-to-one mapping of the kinematics. So it's local, meaning that the kinematics of partons is mapped into the kinematic of hadrons locally. What that means is just that when you look at the spray of hadronic activity that is coming out of your detector, you don't see quarks and gluons, you see hadrons. And those are the ones that are coming out in jets. So given our calculation here, there seems to be a one-to-one mapping between the momentum structure of those objects and the momentum structure of the constituents. So first of all, you want to map the kinematics of those objects. And then second of all, so you want to map, since what is coming out of this discussion here are objects that are colored, while what is coming out of the events that you see at Collider are colorless. So the hadrons are colorless, while these objects are colored. So you have to have a way to map the color of these things, right? And see, here is where the distinction is sometimes is made between, for instance, the first one and the last two, is you can adopt what is called a string tension model. And we will not go into the details of that, but I just wanted to mention it to you. Or you can use a clustering model. The first one is used by Peter, the other is used by the other two. The first one is very much based on ideas that then proliferated to string theory itself, right? So you define a tension of your hadronic interaction. So here you have all your partons coming in, and there are quarks and gluons and etc. Let's see, etc. And you connect them by some strong interaction. You define some strong interaction string tension over here, and then you analyze with your model when this is going to break. And so wherever it breaks, you define hadrons. In the other case, you have an algorithm. In the clustering case, let's do it on this side. You make sure that you split all your gluons into quark, because quarks have color and anti-color. And then you combine pairs of quarks and anti-quarks into hadrons. This is really very, very vanilla kind of explanation, or no explanation at all, but just to tell you that there are algorithms that introduce, that map partons into hadrons. And the uncertainty that they are introducing in our calculation, I will show you examples of that, is not large, it's actually very small. I wouldn't say under control, but it is apparently small. Because we can look at things like the multiplicity of hadrons, and we can calculate the multiplicity, for instance, of the average multiplicity of gluons, or the average multiplicity of hadrons. And they really map one-to-one modulus a rescaling factor. So we really seem to be able to map the multiplicity of partons into the multiplicity of hadrons in a sort of we cannot really explain, if you want, from first principle, the proportionality factor or the mapping factor, but it's there. And so once we have experimental data that tells us how to rescale the multiplicity of partons into a multiplicity of hadrons, the uncertainty we have in this kind of algorithm is very small. Thanks to the fact that most of the dynamics is dictated, as we have seen, by the initial hard scattering. Now, why is dictated by the initial hard scattering? Because the rest is, as we have seen, we can control by collinear and soft dynamics mainly. Now, As I was suggesting at the beginning, and this is the last remark that we wanted to do about the final state radiation, so the evolution from the hard scattering to the formation of hadrons, is the fact that, as I have already alluded to, Parton showers have their own limitations. So Parton showers are correctly reproducing a very particular kind of dynamics, which is the collinear and soft one. So if we have a hard processes that are that have a more complicated kind of hard initiated dynamics, we cannot allow the shower to model them. So we need to calculate them till the point in which the hard dynamic of the process is fully described. So we would do a better job than the idea comes to say, for a process like not E plus E minus to, even for a process like E plus E minus to QQ bar, wouldn't it be better for us to calculate exactly E plus E minus to 3 objects and then let the shower go, than not let the shower go from stage 0. So in other words, wouldn't it be better to have to let the shower start on from the full order alpha S calculation instead of the calculation of the previous order? Or even better, wouldn't it be better to let the shower takes on from even the next level, the order alpha S square, in which at that point we would have calculated exactly 2 orders of radiation, and then let the shower go. So in the moral of this is just, can we push the interference with the shower farther away? So describe the hard emission, the full emission, both soft and hard, exactly at the highest possible order, and then from there on, let the shower go. Of course, yes, right? Because the more you can do exactly, the better, right? And this is the idea of all the NLO Parton shower event generators. Things that you may have either used or heard or seen cited in different talks that are things like MC at NLO, which means exactly Monte Carlo at NLO, or POWEG. Those are 2 main methods that are normally used to interface a higher order calculation with the shower, not at the first order, but at the next order. So things like MC at NLO or POWEG are just methods that assure you that you can take a next to leading order, where next to leading means whatever it means process by process, a next to leading order calculation that therefore includes exactly the first order of radiation and you match it with a Parton shower next, from the next order. From, let's say. Now, this matching is the delicate part. That's why you need a framework that has implemented it for you. Because clearly, the shower wants to emit things, and therefore you need to make sure that when you interface the 2, there is no double counting of emission. Right? So since one of the emissions has just been taken into account by the fact that you are doing your calculation in next to leading order, so for a given process, you are already including this kind of radiation from in your next to leading order calculation, both soft and hard. You need to make sure that then when you interface with the shower doesn't take this process and put on its own little radiation there, because you have already included it. So you need to subtract these from your calculation or from the shower, right? From the shower interface. And the procedure is conceptually very simple, Now, if you look at how this is implemented in reality, it takes some subtleties, right? But it's very well understood and very well implemented in two slightly different ways, into these two different frameworks, if you want, or using those two different methods that you can also use in something else that is neither one of the prepackaged kind of software that is given to you, because it's just a method. So you can implement your this method in your own code if you want, right? So this was just to review for you everything that we can say, right? And as you may see, there is a lot on which we could spend individually and then many more classes, all right? Because all these things, pattern showers, event generators, as well as this method to interface the higher order calculation with the shower, they include a lot of technicalities that have a physical meaning, right? But also, so if you ever looked at, I don't know, the manual of one of these objects, it's mind-boggling, right? So there is everything that you could possibly imagine, right? To a level of sophistication that is clearly way beyond what we have discussed here, but it doesn't also make much sense in the full description of collider physics to start from there. So you get to that level of sophistication the moment you really want to use it. But you know what it is. So you know what it does. You know why you're using it, which is the most important thing, right? And then you get to the technicalities and you decide if you wanted to use tune A or B or C or whatever, because and how it has been obtained, that sometimes it's very baroque, sometimes it's very outdated, sometimes you should be very careful in using anything you're using and never take this for granted. In particular, if you're claiming that you're calculating anything for percent precision at the high luminosity LHC. Okay, so this is another thing that you should learn here, right? Not to take anything for granted, because some things are just there historically, and they're used over and over and over, but they may be introducing errors that are much far bigger than what we claim to be calculated or what we do calculate, including higher orders. So since you are the ones who are going to go out and calculate things or measure things for the next 20 or 30 years, when the high luminosity LHC will come and measure things at a high precision, you better be careful about all these things. Don't think that things so far have been done perfectly, because they have not. They have been done to the level that we needed to do them, right? But now that we are getting to higher precision, never take anything for granted, right? Many things have been done with some level of approximation that was justified so far, but may not be justified in the future, right? So it is really important for the people that are coming in right now to really question what we have been doing so far, right? So in the rest of the lecture, I wanted to move to the other part so that tomorrow we can really, so I wanted to now go back and consider the initial state, right? And therefore connect us to pattern distribution functions, because that is the other element that we need in the discussion of collider events, right? And I will leave this here, maybe taking away the part that we don't need, but I wanted to leave these two kernels here, because now we are going to see the difference with respect to what happens in the initial state case. And we are going to see why that is slightly different. And we need to do things in a slightly different way. Because you may be there thinking, okay, now I know what she's going to talk about. She's going to say, well, this has been our hard scattering. This is the hard scattering. And now we are going back to the protons on this side, and of course on the other side as well. And we are going to talk about the effect of perturbative QCD in the evolution from, again, a scale which is the scale of lambda QCD, or the binding scale of the partons in the proton, and the scale Q of the hard scattering. But we have already seen these in going forward. So what is going to change? QCD radiation has the same properties, yes. It has the same properties, but there is a little subtlety here that we needed to take into account, and it's the fact that when the pattern that is coming in, so the radiation modifies here the momentum coming into the collision. And therefore, it modifies the center of mass energy of the scattering. So we said that this guy is coming in with a certain fraction x of the momentum. But if there has been radiation before that, clearly I need to define how this x is connected to the actual x that came out of the proton. So it's degraded by the radiation. So let's see it explicitly in these two cases, but now where our hard parton, so the parton that we will consider to be, let's say, a quark for our example, is in the initial state, not in the final state. So it's coming into the X process, not out of the X process. So it's one of the incoming partons. So what we wanted to consider is this situation here, right? So, so when this is not to confuse with, so let me, where did I put the red one? Here. So this object here is not a proton, right? So it's clear that it's my red thing, this one, right? So here it will be the same. So it's some hard process, right? So, but now, whatever this is, let me draw it twice because I wanted to make the difference with respect to the situation that we had yesterday. So the situation in which we look at both the real radiation and the virtual corrections, right? And I'm drawing just one leg just because it's, it can be done this way. I can lump both the real and the virtual just in this way. So, so this is the momentum coming out of the proton originally. So here there is the bound state. Here is the object that is coming out of the proton, and the same is here, right? So here I wanted to do the real, and here I wanted to do the virtual. So, sorry, if this parton comes out with some fraction x of the momentum of the proton from here, and then I emit a k from there, this object here will have a fraction of the energy of the proton that is smaller than x. So it changes that particular construction. So in the, I'll try to condense the discussion that we are going to have. So see if the formalism can, if I can skip a step, but probably not. Probably I want to do it. Oops, too many things on my ears. Okay, it's working now. Okay, so just to show you the difference with what we had in the other case, right? So okay, so let's do it this way. So in this case, so let's take that this is coming with, and probably it's easier to directly see it this way. So in the case that we had here on the blackboard, let me, instead of having the glue on here, draw here the virtual part, which is, I wanted to, let me denote the virtual part. This is just, if you want, descriptive, like a correction to the external leg that is a virtual correction. This is just denoting the fact that in this calculation I've taken into account both the real emission and the virtual correction. So the momentum here is P, and yesterday we saw that in calculating these in both the real and the virtual case, we would obtain that this guy would contribute in the soft and collinear region, something that would cancel exactly, because the cross-section that I had here was a cross-section of P. Right? Or if you want, where P denoted the fact that it was a cross-section that had, in this limit, the same momentum, was evaluated with the same momentum. Now, if I look now at the case that we have here, so let me consider the two analogous situations. And now I'm calling this P, but we will see that later we will shift these to the XP of the case. Now, the radiation that is emitted here will be this K, and the remaining pattern will have a fraction of the energy of the momentum here. Let me call this Z. And the remaining here will be, or 1 minus Z times P, right? So when I go and, this is becoming very difficult. When I go and calculate the two different, when I calculated the two different cases, I'm in exactly the same situation. So the calculation that I do, sorry, let me, kind of easier for me to go this way. You see immediately that if you just go through the same calculation that we had yesterday, and nothing else changes in this case, so you can rebuild exactly this matrix element as we built it yesterday, and you can build this other matrix element as we built it yesterday. And you would obtain here something that is exactly of the same form. So it has a 2 alpha S CF divided pi. Now, I can build it with the same variable, or change variable as we will do in a second, but that is not going to affect much of our calculation. And let me even simplify the notation. Later on, I will just use an angle without labels. And then the cross-section that this will be multiplied will be a sigma x of ZP, because the momentum coming into the process now has been modified. And here, you would obtain exactly the same kind of result with the minus sign as we had there, but in which the cross-section that you're multiplying these two, so it's exactly the same form of factorization, but multiplying now a cross-section that is, as yesterday, a function of P. So the big difference between what we did yesterday and what we're doing today is the fact that these objects here, so the objects that factor out the soft collinear part are the same in one case, and they're different in the other case. And they don't go to each other exactly when in the limit in which the energy of this guy becomes the energy of the incoming pattern. So this is most of the problem. So the problem is such that when we put together these two parts, so when we put together both the real emission, that is this part, and the virtual emission, that is this part, we do not obtain a full cancellation. So when I now build the sigma total at the order that I want, let's say at order of S, as we did yesterday, and we put together the sigma real plus virtual in the IR plus the sigma finite, this is fine, but this part here, let's see how we can write it kind of explicitly, pointing out to the fact, pointing to what is going to be the mismatch between the two. And the mismatch between the two is exactly here. Here there is a mismatch. And you can understand why there is a mismatch, because this is not, first of all, as inclusive as we did for the final state, because we are taking a particular parton coming out of the proton, and also because the radiation has happened before the integration. So when it is customary to make contact with the variables that are normally used in parton distribution functions, it is customary now to rephrase or to do a change of variable from what we used there. There was the omega k and the theta angle, the theta kp angle, as I called it, to do a change of variables to the fraction of the longitudinal momentum that I used here to parameterize k and p, just saying this momentum p gets split into zp and 1 minus zp in these cases, and the transverse momentum, what we used already in our, which is kt. And the relation between kt and the angle is already here, is what we used there. And the relation between omega and z is the one that we have outlined. We have already used in our derivation in stating the rules of the game over there. So saying that the k is 1 minus zp, right? So that tells you that omega k is 1 minus the energy p. So if I change these measure into the one expressed in terms of dz and dk transverse, you can do this little exercise of calculating the Jacobian, and you will see that your measure becomes dz over 1 minus z, and then dk perp, or dk transverse divided k transverse. And often you will see this written also as dkt square over kt square, and if you just express that, this has the effect of taking away this factor of 2 in front of your kernels. So I will re-express in the integration that I'm going to write next. I'm going to use the zkt notation instead of the d omega d theta notation that you have there. So in writing this object here, for the process that we are calculating, so for the always for the QQ bar and QQ bar per glue and coming from any plus and minus that we have there, I will write these as therefore an alpha s CF over pi factor, and then we would have the integral in dk transverse square over k transverse square that goes up to the energy q square, in this case, of the hard process. You would have the integral in dz over 1 minus z that indeed goes up to 1, starting from 0, and 1 is the problematic point. You see that when z goes to 1, the z going to 1 limit in our variable is the soft limit, as well as the kt going to 0 is the collinear limit, just to say how the omega going to 0 and theta going to 0 map into the new variables. And here you would have the difference between the two cross sections that we have written there. So there you would have the difference between the sigma that I call x there, that in the case of the process that we are considering is the QQ bar cross section for as a function of zp, minus the sigma x, that in our case is the QQ bar, as a function of p. Now, what happens in this integration is just that the part in dz, so this part here, actually is finite. And it's finite because the difference between the two cross-sections in the soft limit, so in the limit of z going to 1, developed a 1 minus z terms that cancel exactly the 1 minus z terms that you have here. So you're fine for this part of the story, but you're not fine for the other part of the story. So this is the part that leaves, even in the compensation between real and virtual, it leaves some oddity or some illness in the lower bound of the integration. So in the integration that here should start at some scale that clearly is where you have problems. So that scale is a scale that it's a low scale. It's a scale where you meet the proton. It's a scale where QCD becomes non-perturbative. And then at this point, what is so what is done, as a matter of fact, is to introduce a cutoff. And the cutoff that you introduce is the famous factorization scale. So you cut the lower bound of this integral to what we call the factorization scale, in this case a square, because it's the lower bound on integration in kt square. And you can be saying, okay, big deal, right? So I could do that, right? So thank you. So is this solving any problem? But if you think it a little bit more, this is not so outrageous. It's actually pretty interesting. Because would you expect to be able to put a cutoff, to calculate that cutoff meaningfully in perturbative QCD? No, because you're going to a regime where whatever you're using is not the right thing, right? Because you're going to a regime that is the regime of the parton coming out of a proton, so the regime of the parton bound into the proton, in which you should not be using perturbative QCD, right? So what that cutoff is telling you is just that it's kind of measuring your ignorance of the problem in this regime, so in the regime that is getting closer to the binding energies of QCD, which is what you can do at the moment unless you were able to calculate everything from scales even below that, from the binding scale of partons in a proton up to the scale of the hard interaction exactly, which is what you're trying to do when you use lattice QCD, so to calculate the parton distribution function from first principles. Then there should be no cutoff, but there will also be no divergence. That's the thing. So you would not need a cutoff. You would have just the calculation of the dynamics of the bound partons into a proton just evolving, transitioning to free objects with the evolution of the coupling constant. Now, it's a big plan, so it's not something that, but technically you can put QCD, you can develop a first principle theory of strong interaction just as the lattice QCD does, right? Now, there are other problems in calculating things that way that are constantly being improved, and actually parton distribution function on lattice are being calculated. Given our approach, that is an approach in which we can only calculate the evolution of a parton that is already out of the proton through QCD to higher scales, or better, from higher scale to lower scale, we expect to get to a point where whatever we are doing cannot be done anymore. And so we better put a cut there and saying whatever I'm doing is the correct things to do up to this factorization scale here, right? It's up to mu f square. And then this is the lower bound of my integration. And this is what we do here. So we put here a bound, so at this point, which is precisely mu f square. Now, the next step that we wanted to introduce now is just that even having done this, I haven't still completed my plan. There was the plan of now knowing how to evolve that object that will have clearly a non-perturbative core down here. So in the part below mu f, there will be some distribution function, some probability of finding an hadron coming out with the fraction x of the momentum of a proton that is what in our formula we called f h j x mu, where the mu were both the factorization scale and the renormalization scale. But I still don't have a way to connect this object with what I wanted to use up here. And so this is what comes out of just the realization that what we have done here can be repeated. So exactly as we had a parton shower that would evolve the partons coming out of the hard interaction to the energy scale in which we would match with hadrons by further emission, here we can do exactly the same. So we can say that the density of partons that we have calculated here, so the first branching from a parton coming out of the proton to a parton and a gluon can be repeated over and over. And so we can think that, for instance, an object that is coming into the hard process, that we have outlined in red there as a quark has maybe come from another quark that has emitted a gluon, but maybe this quark can have come from a gluon splitting into a quark and an antiquark. And so there is a history before this. And the important thing will be to connect the evolution from the factorization scale to the scale Q, or Q square, mf square, as we have introduced an energy scale of our process in following step. So what we really wanted to have is the evolution of these objects. So it is not difficult to write it, and this is the famous DGLAP equation that you can calculate just by looking at how following steps behave with the branching of this kind. But basically, what we wanted to do is exactly what I drew there on the blackboard, more systematically. So let's look at this last step as our at the conclusion of our discussion. So let me again draw the two cases. So here is our evolution, our pattern coming in. And I'm simplifying things just with one kind of pattern. So we are putting a cut, a lower bound to our integration of KT. And we are evolving up to the scale Q square of our process. Right? And in here, there is the emission, both real and virtual. So I'm just placing what is happening in the context of what we are calculating. So what we are used to do is just to say, this object is coming with a fraction xp. It has emitted this object that has a fraction 1 minus z of this momentum, as we saw there, and is continuing as a z times xp momentum to the process. Now, it is customary, however, to simplify your life a little bit and then rescale everything by z. So you divide these to be that in such a way that what is coming in is the xp. That sounds very much like what you would do, our formula, our original formula, right? So, sorry. This was already an xp. What I wanted to rescale is here. So in here, I will rescale these by z. So this will become that, and this will become this in such a way that this is an xp, and we are happy because both are coming in with the same xp at that level. And then if I have to calculate, remember the formula that we had on the blackboard yesterday, so the formula that would calculate the cross-section as an integral over the dx1 and dx2 of the two parts with a sigma hat that was a function of x1 and x2 and etc. Right? And here we would have the f of x1 and the f of x2 written in a very quick way. So we are concentrating on one of these objects here. And so the sigma that we are writing, if we now consider also the probability distribution in X, and so we write the sigma in the form that we have written there, we would have the sigma for each one of these objects to be the integral over dx of some f of x and some scale. That is our factorization scale, times a sigma hat that is a function of xp. Now, this will be our sigma 0. So in the case in which we don't have consider, so if we just start at this level and we not consider what is happening before. If we start considering what is happening before, we have to pull in these two new objects, and this will give us the order alpha s case, so the sigma 1. And the sigma 1 will now be, apart from the integral in dx, I will have the integral that we had that we have already considered here in dk transverse over K transverse that has now been regulated between mu F square and Q square. I would have the integral in dz of the 2 over 1 minus z of the two objects that we have written there. And actually, because of our rescaling, this rescaling is also bringing in for us some further manipulations that we have to do. And this will, of course, multiply the F objects that we have omitted so far because we had never brought in the integration over dx, right? So from the expression that we have written here, we can now observe that we can write a differential. So we can write the evolution of this object here that depends on the cutoff that we have introduced. So with respect to that, so from that we can say that the evolution of the f with the mu f square, so with my binding or bounding of the distribution function is given precisely by the expression that we have here, including the integration that I have written. And depending on the particle that you are considering, if you work out specifically the steps of, if you identify your objects with what we have on the blackboard, and you work out the step of the integration, bringing in the exact dependencies of these functions on z and on the k-perp that here has been factored out, but could be completed by not using an exact collinear approximation as we have worked there, you will see. And this, because of the change of variable I was alluding, is indeed an argument of x over z. You will see that you can write this differential equation that will take away the integration over dkt square over kt square that we have there as something that is that has a here I have omitted that there is an alpha s over pi in front as an order alpha s object that then multiplies the function, the distribution function itself with a prefactor that is a function of z. And the prefactor in our case, I will call it a p sub qq of z. It's a function only of z. It has labels that are induced by the kind of emission that you are considering, so the kind of splitting of a parton into a pair of partons that you are considering. In our case, is a quark going into a quark. And it does that with the function z of the momentum of the original parton, with the fraction z of the momentum of the original parton. These functions that are obtained from this integration that I've written here are called splitting functions. And of course, you have splitting functions that in our case have been calculated at order alpha s in our calculation and have been calculated for the case of a quark going into a quark. So this gives you the dynamics of a quark transforming into another quark with the emission of a gluon. In the very same way, you can calculate splitting functions for other transitions. So you can calculate a splitting function for the transition of a gluon going into a gluon with the emission of a gluon going into a quark with the emission of another quark. So if you take into account all the possible combination, this will give you a differential equation, which is the differential equation for the evolution of both the parton distribution function of a quark or the parton distribution function of a gluon with a matrix that has the splitting of a gluon as a quark as obtained of a quark, the splitting of a quark as obtained from a gluon, the splitting of a gluon as obtained from a quark, and the splitting of a gluon as obtained from a gluon. And on the other side. So you have a system of coupled differential equations that are the famous DG-Lap equation that will give you the scale evolution of these objects. So this is indeed the scale evolution that we have alluded to in saying that in this process, we go from the proton to the hard scattering with perturbative QCD. So the non-perturbative part of the story is clearly in the solution of this equation, because the solution of this equation will have to have some boundary conditions. And the boundary conditions that are at the scale mu f, so that are at the lower scale, is precisely the non-perturbative core is contained. That is the initial condition for the evolution of the PDF, or pattern distribution functions, that are exactly this object f that we have introduced here, that appear in the calculation of the cross-sections, multiplied by a factor that is what gives us the evolution of the same objects with further perturbative emission of QCD radiation, how they transform into each other during the scale evolution. Now, we are kind of running out of time, but I wanted to show to conclude by telling you how we control our knowledge of the PDFs. So we do control the perturbative evolution, because this is QCD. As you've seen, we have calculated these factors. We have calculated that for the QQ case. We could calculate them for all the other cases. What we don't know is this initial condition that is in here. Now, however, we can use these objects in the calculation of multiple cross-sections, and from the measurement of the cross-section and using the entire formalism that we have developed in the regions where it is valid, we can fit the non-perturbative cores that are the initial conditions for the PDFs. Those are the famous PDF global fits, right? And I just wanted to show you very quickly in here. I think, I need my glasses to see. It says here is this one. Okay, here it is. So I wanted to show you two things. So the first thing here is the first plot up there with that incredible number of little dots. As you see, is on the axis, you have the fraction x of the PDF and the energy q, that is the equivalent of mu f. Here is a consideration. You always, most likely, you have seen PDF written as f of x and q square, where q square is the scale at which you use the PDFs. And this is because mu f, you can choose it wherever you want. So you can choose your mu f at the scale of the process that you are calculating, okay? And then you can tell me, what is the big deal that you have made about the fact that we can evolve the PDFs from this low scale to up here using perturbative QCD? Well, the thing is just that the fact that we know how the PDF evolves will be used to match PDFs measured at different energies. So we do put the factorization scale to the scale of the process that we are measuring, but then we are measuring PDFs at very different scales. PDFs have been measured at HERA at around 10 GeV or a little bit more. They have been measured at the Tevatron at the TV scale. They have been measured at the LHC at the 13 TV scale, well, reduced to the central mass energy of the LHC. So they have been measured at very different scales. What is important is just to connect them from one scale to the other in such a way that we have, and that we can do using perturbative evolution. So as you see in the plot over there, you see listed measurements from very different colliders. There are measurements from CDF and D0, that is the Tevatron. There are measurements for a lot of, from Zeus and Hera, so from all the different experiments of Hera. There are measurements from the LHC. You see that there are measurements from CMS and Atlas. You see that, first of all, they do cover different kinematic regions. So they do cover different values of X and different values of Q square. So when you get to the LHC, you see how the LHC is now coming in and giving us new information about having measured processes that leave at energies and fractions of X that are different from what was measured before. So this is extremely important. And we can connect them because we know how the PDFs evolve. So we can connect the different Q square because of that. The behavior of the PDF, as is listed here, is different at different Q squares. So you see a low scale of 2 GeV there, you see a scale of 100 GeV there, and you see PDFs that you could plot on your own PC, right, on your own laptop, just using one of the many packages of PDFs that are out there. You can take a PDF from the CTEC collaborations, you can take PDF from the NN PDF collaboration, you can take PDF from the MS, it used to be TW, but now it's something else, ST, MS, I think I've checked what they are right now. HT, that's what they are right now, collaboration, download it and build what is the PDF distribution for an up, for a down, for a charm, from a strange, from a bottom quark even, from the gluon. And you would see that they have those behaviors, so behaviors that are very different when you go to low scale to high scale. You see how this is related to the form of their splitting functions, so how they changed when you go to different region of Z's and to different region of X. So you will see, for instance, like at 100 GeV, so at much higher energies, the gluon PDF, for instance, is dominating, while at lower energy, the quark PDFs are dominating. This is a big impact. It is something that we can verify, so it has a big impact when you go from the same cross-section measured at the Tevatron or measured at the LHC. At the Tevatron, you had a factor of 10 in energy difference. So in one case, QQ bar processes channels are dominating. In the other case, gluon channels are dominating. So this is something very important that you can, and it's all, you can make sense of all these. This is all derived by implementations of our parametrization and understanding of the pattern distribution function, as we have explained here. You can see in the other plot that I have here, two other important things. So the one on the left somehow reiterate what you could patiently figure out from the plot there on top, because it has done the job for you, and it has isolated in here the region of the XQ square space that is covered by Hera, or the previous fixed target experiment, and now covered by the LHC. So the LHC is expanding that range towards lower X's and higher Q square, as you see there. And on the right-hand plot, you see something that we will use tomorrow, because tomorrow we will, or it connected to the discussion that we are going to have tomorrow, which is to put together everything that we have seen and just say, okay, now we know the full picture. We have seen how we can go from how we build the shape of colliders event out of hard scattering, evolved forward and backward to meet the parts of the story that are non-perturbative and we cannot describe exactly. Tomorrow we will discuss how we estimate theoretically the systematic uncertainty that we have in that comparison. So we have laid out the principles. I've told you how good or bad we could do in doing that. And we will see tomorrow how quantitatively we can estimate the kind of systematic uncertainty that we have. Now, the PDF, of course, will come into the game because for Hadron Collider, they are the starting point. So they are one of the components in the equation that we had here of our predictions. So we need to have them under control as well. And so what this plot is showing for you is just the uncertainty that we have on the PDF from what we control, which is the evolution of the PDF, when we play the game that we have seen here, including different orders of QCD corrections. from the leading order to the next to leading order to the next to next to in the evolution. And you know how to include them. So including in the evolution would be considered 1 emission, 2 emission, 3 emission, and the corresponding virtual correction in a simplistic way, right? This is different components come in, but just putting in consistently different layers of QCD correction. And you see how crucial that is, right? So you go from having an uncertainty in certain regions of X that are pretty broad to squeezing those uncertainty at the level that nowadays introduced from the PDF an uncertainty overall, depending on the process, et cetera, that is never more than a few percent. So even if in that game we do have a non-perturbative component, but the amount of knowledge that we have about how they come into the game allows, and the precision that we have on the other hand from experimental data that we use for the fits, allows us to keep control of those objects at that level. Okay? Okay, so I'll stop here.
Hi. So, well, thanks for the lecture. I have 2 questions. The first one is regarding the limitations of the Parton-Shower algorithms. What's the bottleneck for this type of calculations? What's the limiting factor?
Well, the Parton-Shower calculations are also improved, are also being improved. It's probably one of the, if you want, most difficult aspects on which to really control systematically, quantitatively. But mainly because of the implementation of the principle into the practice. Like I was alluding to the fact that the PITIA manual is 200 pages of things in which there is both sound first principle implementation and a lot of alchemy in how to do things, right? But leaving all that aside, just from the first principles, Parton showers can be improved in the part that we control, so before we get to hadronization, and when we get there, using as much as we know the mapping between Parton and hadrons, mainly by controlling the evolution, right? Mm-hmm. And so these splitting kernel can be calculated at higher orders. The probability factors that we have used here can be calculated at higher order, and this is done these days. So Parton showers are, as we will see tomorrow, a very crucial thing is to try to be consistent in the matching of all the pieces. So the matching of the hard scattering with the evolution from the PDF and with the evolution of the Parton shower. So when we go up in order, QCD order in one case, we have to consistently go up in order in the other cases. And at the moment, Parton showers have almost completely including next to leading order corrections in QCD, and resumming large logarithm coming from the collinear dynamics that we have here to the corresponding order, which is the next to leading log. So for the QCD part of the story, they are being improved. And that part gives us a control on the precision of the results that is comparable at the few percent level with the rest of our calculations. There is another big chapter, which is on the other hand, how these tools are used. Mm-hmm. And that is a different story that, however, I will not really put into which kind of theoretical precision we have, but in how the tools, which kind of care needs to be taken in using these tools.
Yeah. Thank you. And my second question is, well, could you comment on the use of these type of algorithms for E plus E minus low energy colliders? Because intuitively, I don't think it makes a lot of sense, right? Because, well, you don't have showers and as much QCD. But, okay, not Sherpa.
So E plus E minus low energy.
Low energies, yes.
Low energy.
Because Sherpa, for example, at low energies doesn't use it, but there's some Monte Carlo that use these type of algorithms. Does it make sense to do so?
So which kind of Monte Carlos do you have in mind?
So Baba Yaga, for example.
Okay. Well,
I'm not sure if it's just the idea and the name that it's the same and it's totally different thing, or...
Yes. So those tools that you have in mind, let's say for E plus E minus colliders in general, there is not there hasn't been done a corresponding level of effort as for hadron colliders because it wasn't considered like something really needed, right? Now, of course, for low energy experiment, there is in a way less need because, as you said, there is less space for the evolution. For the plus and minus colliders at high energies, there will be need for these things. They're not very developed yet, right? So,
Thank you.
sure.
Okay, one last question, then we'll go to Q&A.
Okay. Yeah. I was wondering, how do you exactly interpret this mu f squared? I mean, is mu f squared is bigger than q, or is it smaller?
It's bigger in general,
Okay.
meaning that it's above it. It can go till q, this q.
Yeah.
Oh, no, okay. It's bigger than the Q0. So it's bigger than lambda QCD. It can go down to lambda QCD if you want. It can go up to anywhere here, right?
Oh, so it's smaller than the hard scattering q.
It's smaller than the hard scale Q. It's a scale between the binding scale and the hard scattering, but it can move.
Yeah,
in
because
here.
that's what I found a little bit confused because when you drew this diagram, this similar diagram for the Parton shower, I interpreted it as the Parton starts at the scale Q, it evolves until the lambda QCD, and by losing energy by scattering, and then okay, but here, how is it gaining energy? Like it starts at the scale of mu f squared. And then it gains energy until
No, this is just, it's slightly, it's not the same perspective. I mean, the diagram is not just evolving in energy in the two cases. Here is just going from the scale in which the partons are bound in the proton, that has to be, to the scale of, to the energy scale of the collision, so to the energy scale of the hard scattering, that is where the partons are brought by the fact that we are accelerating this proton and smashing them against the other at those high energies. And those high energies are the energies with which we can see inside the proton because we are really looking into the constituents. So because QCD, strong interaction at that point becomes weak, right?
Yeah, I'm still a little bit confused, but maybe we can talk.
Okay.
Yeah, because
Okay.
time's up.
Okay, maybe we can stop here. Let's thank Laura again. And we'll resume in 10-15 minutes.